Hello, my name is Bob Hengstebeck. I am with the Materials Characterization Lab at Penn State University. We're having a discussion today about a new capability within our surface analysis lab. So let's get into today's topic, which is a new ion gun source that we have, which is a large gas cluster ion beam source. And why are we excited about it? I'm very excited about this new capability. And the reason for it is that in the surface characterization technique XPS, or similar techniques like TOF SIMS or Auger, the typical information depth that we're working with is in the 3 to 7 nanometers level. So just a few model layers of material if we're the signal that we're going to be analyzing. And for most materials that we go to analyze, they have to be handled and they have to come in with some kind of container. And often people like to put the samples just in a plastic bag. And a lot of these plastic bags end up having some kind of a release agent inside of them, and they leave surface contamination or just sitting in the air. And those materials have a polar surface, and a lot of organics that are in the air are polar, and they'll be absorbed on the surface. In fact, it's the term that leads to something called adventitious carbon. And so it's not rare to have these surface layers, such as shown in the example A, be greater than our information depth. And when that happens, the photoelectrons that we're generating with an X-ray source, which can go quite deep into the material, the photoelectrons don't have enough energy to escape so that we can detect it. And if there's a layer of interest we want to see, we want the sample to look more like B. And the question becomes, how can we clean the sample without changing the chemistry of the surface and remove that surface contamination? There aren't a lot of great methods. And so this GCIB is turning out to be a new method for doing this and a pretty good one. But let me get into why that would be. So one of the ways that we can go about cleaning our surfaces is using an ion gun. And so this is typically something that people have gone and used for many, many years. But the traditional ion source has a monoatomic source. And what that really means is we're going to take a single atom or molecule. So maybe in this case argon, or in the cases of oxygen, O2, and we're going to ionize that species, and we're then going to bombard it onto the surface. The new GCIB source is going to use adiabatic cooling. And so essentially they're going to take a high pressure of argon, they're going to pass it through a very small aperture into a low vacuum side and speed up that argon going through to subsonic speeds. And in that process, you get supercooling. And that allows you to create these clusters. And depending on what the original pressure size, what the cluster size, and what the vacuum was before or after the aperture, you can basically tune to different cluster sizes. So you can have as small as 50 atoms, or you can go all the way up to 10,000 atoms. We're not going to be working in the 10,000 atom range, but you have this ability to control the cluster size. And as we're going to show in the images, in this image A there, which is being a slide that I have borrowed from a source that's listed here, if we were to use the standard monoatomic gun and sputter into the material, the actual sputtering process is something called a collision cascade. And we're going to show an example of what that looks like in the next slide. But the actual sputtering occurs by essentially uplift of the material that are then from well below and pushing the material out. And those interaction depths, let's say at 5 kV, is about 15 nanometers. If our information depth is on the order of 3 to 7, and we've damaged the material up to 15 nanometers, we may have changed that original surface that we wanted to look at. We've lost the chemistry. And that's actually normally what happens. And I'm going to show you an example of what that looks like. The new GCIB source, it works very differently. For one thing, the large clusters, because of the size of them, they actually come in at a much lower velocity. On top of that, the clusters themselves being supercooled, they break up very easily and allows a lot of that energy to be spread instead of directly into the material towards the tangentials or away from the surface. And so we can essentially get it to the point where any kind of subsurface damage that occurs is within the information depth or some very minor portion of the information depth that we're going to analyze. And I said, we'll show that and how it looks in the couple slides going forward. So we're going to spend just a moment here talking about what happens when we use a monoatomic species or a traditional ion source to sputter our materials. And anyone who's talked to anyone using XPS will say, hey, you may lose the chemistry. And this is really what they're trying to get at, is what you're seeing in this slide. If we look to the left, there's a simulation of what happens when you take a 5 kV argon ion and you hit a surface and then allow it to sputter. And you're looking at what happens at the initial sputtering event in the bottom slide, which is only occurring within a few femtoseconds. What you're going to be seeing in that image is a huge amount of cascaded events and a lot of subsurface damage just to get that little bit of sputtering to occur. What does that mean in terms of our materials? Well, this is a good example. This is real data taken from iobium 205 single crystal material, where we've sputtered it with a 2 kV argon species. And essentially, we see almost it was with that first sputtering event, reduction from +5 to +4 towards +3. And so we actually can show that as documented in the lower slide, that as we sputter continuously, we lose the +5, we start developing more +3, and we even have some +4. Eventually, it'll go all to +3. But essentially what's happened is we're preferentially sputtering oxygen and changing the chemistry. So if we had an organic coating of a surface and so you wanted to know what the chemistry was at that interface, and we had to remove all the organic, by the time we got down to the actual interface, all we would see is this cluster of Mb +5, +4, and +3. And you'd have to ask yourself, is that real? And this example is showing you it wasn't. So now we're going to talk about what happens when we're using the GCIB cluster. So again, we're going to be looking at a simulation here, and this is a simulation that someone else did, and so there's a reference to it towards the bottom here. And it's a 10 kV argon, it's about a 500 atom cluster. And the clusters that we're actually going to be using more in the lab are going to be much larger. They're going to be anywhere from 1,000 to 2,500 or 3,000 atom clusters. But in this example, you'll see instead of getting large amounts of subsurface damage, you essentially push the material off to the edges, and then you got some sputtering. Almost all of the argon that actually hit the surface actually was removed during the initial breakup and collision of the material. And you'll see that again in that picture. But what would happen then if we go back to that same Mb205 and sputter for a long time? Well, as it is, we're not seeing any +4, +3 generation. There is a very small amount of subsurface oxide that's still being formed. And again, that was showing in that damage layer of probably less than a nanometer. And it's showing off as a little tiny shoulder to the right of the niobium +5, if you look at it there. And to give you an idea what that looks like in terms of percentages, I actually had to multiply that by 10 to be able to show the graph that you're looking at on the right. A practical example with a difference of what would happen if we were sputtering an organic material with a monoatomic gun versus the GCIB source. And so for this example, I'm going to take a polystyrene that has a TiO2 filler. Basically, the filler makes the material white. And I'm going to sputter it initially with the 2 kV standard source, which is a single argon ion hitting the surface. And you'll see in the picture to the left that the sample right away went from being this whitish color to this dark color. What's happening is we're actually taking that polystyrene and we're turning it into graphite or a graphitic carbon. And that's actually what's shown in the middle picture. And that orange you're looking at is a representation of what we see, and it also fits the chemistry of an amorphous carbon. If we then turn off that gun and turn on the GCIB source, we'll actually see the material recover. And it'll go back to being this white color that we would expect to see if we're kind of profiling the material. We completely removed all of that dark coloring we were seeing. But more importantly, we start seeing coming out of the material titanium and oxygen. And that's actually from the material. If we just make a plot of just the carbon species, whether it be an amorphous versus what we expect for polystyrene, you can actually see a transition of that in the lower slide. So not only was I able to make this material recover by going to the 10 kV, but I was able to keep the chemistry. Polystyrene is actually a unique material for kind of showing this example because it is uniquely known that if you have to sputter it with an ion source, it very easily can be damaged. And yet the GCIB is not doing this. All right, so let's take this back to the original example that I was showing you, where we had an interface oxide that we wanted to get an idea of what was happening with it. That specific oxide actually had a suspected contamination layer, and yet there was a coating on it. And that coating, and we needed to remove it to be able to look at that interface. And this is actually an example of a material that was known to have a delamination issue. And so had we tried to sputter this with initial 2 kV source, a couple of things actually happened. One, the sputtering was very, very slow. And so it took a long time to get through to the interface. But also, that material, just like the polystyrene, formed an amorphous carbon, and we actually lose some of the information that was in the coating. We'll talk about what that looks like in a moment. But essentially, we lost that information. And then when we finally did hit the interface, we got through the interface so fast that we couldn't actually see what was going on. When we go to the GCIB source, well, now all of a sudden, we're actually sputtering that coating much faster. This actually is something that's uniquely found about these GCIB sources. They sputter organics very quickly, where the inorganics sputter very slowly. That's actually shown in the bottom right image there. And in fact, if you were to ratio one to the other, the organic portion to the inorganic portion, what you would find is that organics are sputtering at anywhere from 1,000 to 10,000 times faster than the inorganics. Again, you might ask, why am I so excited about that? Well, that means I might have a way to very quickly clean off the organics that might be an adventitious carbon or a contaminant layer on the surface and preserve the surface that you're actually asking me to analyze and keep its chemistry. We'll take a look at what that looks like in the next slide. So now we're going to have a more practical look at what the GCIB can do for us in terms of this example. So again, we've got this coating with an interfacial material or suspected interfacial material on an oxide on a titanium metal substrate. And we think that there might be this contaminant layer. And we want to know for certain if there is. With the monatomic gun, we couldn't do that. But here with the GCIB source, we can actually very quickly model what the organic is of the coating, create that model, and then subtract that from what's left over, and we'll see this interface region. And it turns out the interface region ends up having a high level of aliphatic carbon, CO, and carboxylic acid. It's not an unusual organic to see in an interface, but in this case, it turns out that it allowed for delamination of that coating on the oxide substrate. So it gave us ability to actually see what was happening here and tell somebody about the material that we have not had the ability to do before now. So let's move on to another practical example. And in this case, we're looking at a material that's been given to us from Dr. Ola Rochwan from Hershey, Penn State. And what her group is trying to do is look at different ways of molding or forming peak materials that are going to have bioactive agents in them for medical applications. And they're looking in this case of saying, we're going to take the material we have, which is a peak, and they're going to have zinc oxide and silver fill. And they want to be able to know, does this mold process allow them to have a bioactive surface? As it turns out, the PDMS from the mold gets onto the surface, and so the initial surface, we're primarily seeing a PDMS contamination, so it's polydimethyl siloxane. On top of that, we're not seeing a lot of the silver or the zinc at that surface. And so if we want to remove that initial contamination, we then want to know within depth, hey, are they getting this bioactive area at the surface, or is there something else going on? As it turns out, the GDMS allows us to see layering into the material. And so initially, after we remove the PDMS, we still don't see very much of the silver, the zinc. And then in that near surface region, we do see a lot more of the zinc filler and the silver filler. We also are able to preserve the chemistry. So we know that the zinc is in the +2 state and the silver is primarily in the +1 state, which is what they wanted to see in this material. And then as we go deeper into the material, we actually will see that it goes down and towards what they're expecting in terms of bulk composition. So the process did allow them to make a more bioactive area once they would do a little bit of surface processing to remove the crust that's being formed during the cooling of the material. And this will be our final example, and we're, in this case, looking at a polymer film stack. And if we are traditionally trying to analyze this with a traditional ion source, none of this information will be available to us. These materials, which are polyethylene and nylon, would very quickly form graphitic material, would not sputter well, and we would lose all the information in trying to do a depth profile. So this specific example, which comes to us from PHI, the manufacturer of our tools, they're looking at this polyethylene nylon, and they're doing two things here. One, on their time-of-flight sims, they were trying to show that they could actually cut the sample in a fib-like method, turn the sample on the edge, and then image the different layers going through. But from the XPS standpoint, they did a traditional profile using the GCIB source, and not only could they see the different layers by looking at composition, but they're able to preserve the chemistry and actually have peak fitting using least squares fitting, where they can look at what's polyethylene, what's polynylon, what's polyethylene and nylon as you go through the stack. And so they're actually able to very quickly show not only compositionally what's happening, but tell you compositionally how much of it would have been polyethylene, how much of it would have been nylon in those mixed layers. That's pretty unique, and it's something we're excited to be able to offer to you. So I'd like to conclude by letting you know that my name is, Bob Hengstebeck. My colleague in the lab is also Jeff Schellenberger. You're more than welcome to contact us if you have questions not only about using GCIB in your applications, or if you have a surface analysis application that might need XPS or OJ, Jeff and I are available. If there are other areas of techniques that you may need for surface characterization, whether it be SIMS or low energy ion scattering, please let us know. We may not have them here, but we have resources that we can direct you to. Thank you and have a good day.